All right, welcome back to differential equations here. So, oops, not 2.4, we are on 2.5. Okay, so we are doing substitution techniques. There are a lot of substitution techniques. And we're going to cover two of them, okay? And they're going to be pretty easy to identify what you're supposed to do. That's one of the problems with the substitution techniques is some of them are kind of off the wall. It's like, where'd they get that? I don't know, it worked. But identifying like when and where you're supposed to use them has always been kind of a challenge. I might put out an optional one. This was one of the substitution techniques that I was taught, but we don't do it in this class. Okay, so let's see here. The first one has to do with something called Bernoulli equations. Okay. I don't think I spelled it right. I tried. No, I think that is spelled right. I won't promise that I'll ever spell it right again. Okay, but Bernoulli equations. And what you're doing with the Bernoulli equation is you're looking for the form. You're looking for a y tick plus some function of x, which could be 1, right? It could be a constant. That's fine. Okay, times y. And that is equal to an f of x, right? So just normal first order linear equations here, right? Except now we're going to put a y to the n up here. Okay, so it reminds us of a first order linear, and we're going to use that because what we're going to try to do is we're going to make a substitution that's going to turn this into a first order linear. Okay, and the substitution we're going to use, okay, is we're going to say let u equals y to the 1 minus n. Okay, you can use any letter you'd like here, but I think u is pretty common. Okay, and then what we're going to do is we're going to get our du, right? And then we have to take the derivative. So this is going to be, right, 1 minus n y to the 1 minus n. And how do you take a derivative, right? We subtract 1 from the exponent. So it's 1 minus n minus 1, okay, dy, chain rule. So this simplifies down, right, to 1 minus n. This is going to be like, 1 minus 3, okay, minus 2 here. And then 1 minus 1, right, is 0. We just have negative n here, dy, and that is equal to du. Okay, so just going off, I'm not going to do this with every one of them because the next substitution technique, this is not the best. Okay, so what's going to happen here is we're going to go ahead and we're going to say, let's solve for dy here. So that's going to be 1 over 1 minus n, right? Y to the positive n because we're multiplying by y here, and then du is equal to dy. All right. So I'm going to make a couple of little notes here. So, right, we need a couple more notes? No, I think we're good. Okay. So we're going to go ahead and use this to substitute it back in here. Okay, so y tick. So y tick is equal to this piece here. So we have 1 over 1 minus n y to the n du, right? That's dy, plus p of x, okay? Y is, what are we doing here for y? Y is going to be, right? Where is my y? I didn't type in for y. Okay, so this is going to be, what am I doing with that? Yeah, we're just going to put in y for a moment. That's it. Okay. We're just going to put in y. Okay, is equal to f of x and y to the n. Okay. So at this point, okay, we're going to go ahead and we're going to, right, the idea here is we want first order linear, and the rule for first order linear was this coefficient here at most could have like a 1 as a coefficient, so that's what we're going to work on. Okay, So we're going to multiply everybody by 1 minus n, right? So we're going to say, well, this is 1 minus n times the whole equation, and then y to the negative n, again, times the whole equation, times this whole thing. Okay, so it's y to the n du plus p of x y is equal to f of x y to the n. Okay, this is negative here. So what's going to happen? We're going to end up with, there's a 1 minus n here. Okay, so all of this stuff is going to cancel. That's kind of the whole point, is we're going to clean off our du, or u prime, plus, now we have p of x, right, over, or times a 1 minus n. Go ahead and make that a times a 1 minus n. And then we're going to have a y times y to the negative n, right? Or 1 minus n, right? This is also going to be p of x, 1 minus n, and this is y to the 1 minus n. That's what we could say here. And then this is equal to, what are we doing here? We are doing a, this is a negative, so we have f of x, right? We have a 1 minus n here. We have a y to the negative n and a y to the positive n. That's going to be y to the 0, so that's going to go away. So we're just going to have this is equal to f of x, okay, plus du. Do you remember what 1 minus y to the 1 minus n was equal to? It was equal to u. So we have du. I'm going to just call this like p1 of x. I'm going to fold this 1 minus n into here, okay? And then we have u, and that is equal to some function of x. And hey, that looks exactly like a first order linear equation, which we know how to solve because we can use integration factor, right? And solve this in u, and then convert back to our y's, and then we'll have a solution. Okay, so that's how we do Bernoulli. I think we definitely need some examples here. So why don't we go ahead and do that, and we'll work through that. Okay, so let's start off with a nice easy one. So I'll do a hard one next. So example 1, we have y tick minus y is equal to y squared e to the x. Okay, so not linear, right? First order, but non-linear. Okay, and you say, wait a minute, there's a function with a y to a weird power here. That's Bernoulli. By the way, this n doesn't have to be integer, right? If we had done that, right? If we had the square root of y rather, that would have been fine. Same substitution, same everything. Okay, so but we're keeping it easy for this one. So we're going to say let u equals, and we have y to the 1 minus n. So we have, this is y to the negative 1, right? So we have, what is this? U is equal to 1 over y, or y is equal to 1 over u. Either way, okay. And I don't think there's like a prescribed way of doing this. I've done a couple of these in slightly different ways, just kind of messing with what I thought would be an easier derivative to take. And other than like my choice of taking which derivative I wanted to, right, with exponents dealing with u or y, they've all pretty much worked out the same, and it's been about the same amount of time that I've done this. So once you've got the substitution in, there are about 8 ways from Sunday to solve this. You're kind of, it's up to you on how you see it, how you see the best way to proceed is. You don't have to follow a prescribed recipe to solve this thing, okay? But one thing we do have to do, right, is every time you make a substitution in a calculus class, we have to take the derivative of that substitution, okay? So we're going to say y tick is equal to negative 1 u to the negative 2, okay? And again, either way you want to do that is fine, all right? So we'll go ahead and do that. Since I've got a y squared here, why don't we go ahead and just do that? Y squared is going to be u to the negative 2 as well. Okay, positive, right? Just multiply it by itself. Okay, let's do some substitutions here. So, du. All right. So like I said, let's do some substitutions. So for y prime, right, dy, we got negative u to the negative 2 du. See my 1 minus n. Okay, and this was a minus y, and y happens to be 1 over u. And this is equal to y squared. So this is u to the negative 2, right? Y squared is, and then e to the x, we're not touching that. We're just going to leave that alone. Okay. And the last time what we did was we said, oh, we have to clean that off. So what we're going to do is multiply by negative u squared. Okay, and that'll make this a 1. So we'll have du or u tick. We'll use u tick on this one. Okay, so we'll have a u tick minus, well, u squared over u, right? That's going to be u. And then negative times negative is positive, so we have u tick plus u. And that is equal to this guy times this guy. We're going to end up with a negative e to the x, because these are going to cancel. All right. So this is shaping up to be kind of a nice problem. Okay. So my integration factor, right? This is going to be e to the what? To the 1 dx, isn't it? So this is just e to the x. Okay. So we're going to multiply everybody by e to the x here. So we have e to the x, u tick, plus e to the x, u, is equal to, looks like negative e to the 2x, right? E to the x times e to the x is going to be e to the 2x. All right. I could swear I had a negative sign or something in here, maybe. I may have lost it. Okay, my example. Okay, let's check. This is the derivative of u e to the x, isn't it? Right, derivative of the first times the second plus the first rather, times the derivative of the second, which is e to the u, is equal to negative e to the 2x. Okay, let's go ahead and integrate. So integrating this guy here, integrating this guy here. So we end up with u e to the x is equal to negative 1/2 e to the 2x plus c. Cute. All right. So the next thing we're going to do is we're going to solve this for u. So this is e to the negative x on everything, right? So multiply both sides by e to the negative x. So that'll cancel out. We've just got a u. We've got e to the x times e to the negative x. It's negative 1/2 e to the x plus c e to the negative x. Right? A lot of times your book is going to do this. It's going to say c e to the negative x minus 1/2 e to the x in an attempt to see if we can't spare the negative sign there, because it's really easy to lose them as I'm looking at my notes here. And then what the heck was u? Went all the way back up here. U is 1 over y. All right, so we have 1 over y is equal to c e to the negative x minus 1/2 e to the x. We're going to go ahead and use reciprocal rule. So we have y, not u, y. So we have y is equal to 1 over c e to the negative x minus 1/2 e to the x. And then since that is solved explicitly in y, we're going to call that good and spare a day for it. Okay. Let's see. All right. Sometimes I kind of like to look at these, okay, just to see. So we can kind of do a Desmos here to see what this thing looks like. All right. So what do we have here? We have y is equal to. We'll do a parentheses. We'll do a c e to the negative, or to the x rather, right? C e to the x. C e to the negative x, put a negative here, negative. minus 1/2 e to the x, and oops, not there, and that's parentheses, and then raise everything to the -1. And we'll add a slider for c, so we're going to see what's going on here with this. All right, it's delightful looking. That one's kind of neat, right? C is -1. Okay, so just a thought, to see what this thing looks like a little bit, but that's our solution here. Okay, how about we try one that's step it up a little. Okay, so let's go ahead and take a look at example 2. Okay, so this is y tick plus y cotangent. Already I'm getting a little worried, right? And that's equal to y to the 4th, oh dear, sine x. Okay, well, we have almost something that looks kind of linear, right? But, oh, it's not linear anymore. So we can identify this and say, Bernoulli, we have a way of dealing with you. So we're going to set u is equal to y to the 1 minus 4, which is equal to y to the -3, right? Okay. Let's see here. So we have u is equal to y to the -3. How did I want to do this? I wanted to say that this is y is equal to u to the -1/3. Does that make sense? If we take the cube root, both sides, multiply by -1/3, we get y. Okay. I also want to make the idea that y to the 4th is equal to u to the -4/3. Okay, that's beautiful. And then here, what we're going to do is we're going to say dy, or y prime, right, is equal to -1/3 u to the -4/3 to u. Okay, so if you were worried, like, does it work on fractions? I mean, it's still, still didn't, right? We still took a 4 here. So the fraction still remains. I don't know. But this is, about as lovely as a problem, right, as we could think of. I'm sure we could get worse, but okay, here we go. So let's see here. Let's go ahead and start replacing things. Do I want to do anything more with this? Nah. Oops, this is y tick. Okay. So let me just go ahead and write this down. We have y tick plus y cotangent x is equal to y to the 4th. What was the sine cubed? No, just sine x. Okay. So we have some substitutions to set up. dy was equal to -1/3 u to the -4/3 du plus what's y? That's u to the -1/3, right? That's y. And then we have cotangent of x, and that was equal to y to the 4th. So that's u to the -4/3. And again, I don't really care too much about the sine and the cotangent. Okay, not yet anyway. That'll come. Okay, the rule was we're going to clean off this first term so it has a coefficient of 1. So what we're going to do is we're going to multiply by -3 u to the 4/3, and that'll take care of all of the problems, won't it? That'll be, no, it won't. Yes, it will. Because 4/3 and 4/3. 4/3 and -4/3 will be 0. So u to the 0 will be 1. Okay, so this all cancels. So we just have a du plus, we have -3. U to the 4/3, right? U to the 4/3 minus 1/3. Isn't it just u? Right? 4/3 minus 1/3 is just 3/3. And then we have a cotangent x here. Okay. And that is equal to -3. Okay. 4/3 and 4/3, right? 4/3 minus 4/3, that's 0. So we just have a sine x. Just like we predicted when we did it for the first time, right? When I showed you, like, without specifics. Okay. And again, look, we have a du, we have a u with a coefficient, and we have a f of x. This is a first order linear equation. And now we have the delightful task of getting an integration factor. So we're going to say rho is equal to e to the, okay, we have negative 3 cosine x over sine x, right? That's what cotangent is. So at this point, we're going to say set v is equal to sine x, and dv is equal to cosine x. So we have rho is equal to e to the negative 3, and then we have 1 over v, that's my sine dv, which is e to the negative 3 natural log of v. Technically, those absolute values here, but we'll show you in a minute. Okay, and then we have rho is equal to e natural log of v to the negative 3, which is v to the negative 3. So this is sine x to the negative 3 power. That's my integration factor. That looks lovely. Okay, so let's go ahead. We're going to multiply this, right? We're going to multiply sine x to the negative 3 on both sides. That's how we do integration factors. Okie dokie. So let's see here. Right, this one. That's the equation we're plugging back into. Okay, so we have sine x to the negative 3 u tick, okay, minus 3. I'm going to go ahead and write down cosine x over sine x times sine to the negative 3 times u, and that is equal to, what are we doing? That's negative, it is. X. Okay, don't tell my trick class. All right, and then equals, on the other side here, we're going to have a sine x, and we're going to have sine to the negative 3x times, oops, there's a negative 3 here, isn't there? Times sine x. I think that's our set there. Okay, delightful. So we have, I'm just going to clean this up a little bit because 2 reasons. 1, kind of want to see what we're working with here. 2, I think it's really important that you guys see this as like when I took the derivative of sine to the negative 3, we got negative 3, oh, those are you here. We got negative 3 sine to the negative 4 times the chain, which is going to be the cosine x. Okay, so I really want you to see that when we took this derivative, this is the piece that we're going to be getting. Okay, u, and this is equal to, well, this is negative 3 sine to the negative 2x, right? I'm going to change that, what that is in a minute here too. So here, right, this is the derivative of u times sine x to negative 3. Okay, so if you're still checking, all right, if I take this derivative, right, that's negative 3 sine x to the negative 4 times the chain cosine x. That's what we're going to have here. Okay, this is equal to negative 3. Okay, sine to the negative, isn't that cosecant squared? Okay, and the reason I want to do that is what's the derivative of tangent? Right, derivative of tangent is secant squared x. I think the derivative of cotangent x is. If you said cosecant squared, you're almost there, right? It's negative cosecant squared x. Okay, so when I take this integral, I'm going to have a nice little form for it because that's one of those that we kind of remember. Okay, and I never remember cosecant. I always remember just the secant one. And then when I get a cosecant, I'm like, oh yeah, I've got a rule. So we integrate both sides here. We integrate both sides here. So we're going to end up with u times sine to the negative 3x. Okay, that is equal to 3, right? Because the negative is going to be sucked up into this integration here, and we just have cotangent x, okay, plus our constant of integration. Okay, and now what we're going to do is we're going to multiply everybody by, right? Sine cubed x, right? multiplying everybody by sine cubed x. There we go. 10. So we have u is equal to, okay, 3, again, I'm going to go with cosine x over sine x for cosine times sine cubed x here, okay, plus c times sine cubed x. Okay, this is really why we harped on you guys for plus c, because now it matters. Okay. What the heck was, oh, let's clean this up a little bit. That's 2. What was u? Like way back about 3 pages ago, right? And 2 substitutions, at least, maybe 3 substitutions. U was y to the negative 3. Okay, so here we go. So here's y to the negative 3. This is equal to, right? We have 3. One of the signs cancels, so we just have, that should be a 3 here. All right, so we have y sine squared x cosine x, right, plus c sine cubed x. So this is going to be a delightful looking function, isn't it? So let's use reciprocal rule. So this is y cubed equals, and then we have 1 over this mess, right? We have 3 sine squared x cosine x. Don't do reciprocal on each one of these. It's the whole thing. Okay. C sine cubed x, and then what we're going to do finally is y is equal to, see all these crazy trig equations that we gave you, like in pre-calc, when I said solve this stuff, I'm like, here's your chance. So, oops, that's a squared. That's not a, right? It's cosine x plus a c sine cubed x, and since we took the cube root, here we go. Okay, you could put parentheses around it and say to the 1/3. I mean, there's all sorts of equivalent ways to do this. You want to do sine, I guess we can't do a sine cosine thing. I guess we could take it sine cosine and do a sine 2x in here, do a 1/2. You could do something like that if you wanted to. I wouldn't recommend it. I think leave it as simple as you can, and that's going to be terrible. All right, and again, I kind of have a little thing of like, what the heck does this even look like? Okay, so let's get rid of that. Let's get rid of that. Desmos here to the rescue. So what do we have? We have 3 sine squared cosine x. So let's go ahead and say u1 equals 3 sine squared x cosine x. Oh, it didn't like that, did it? Oh, I need, okay. There, okay. So that's nice. We've got a u2 equals, what do we have here? We have c sine cubed x. So this is c, oh, we definitely need this one. Sine x cubed, right? Yes, add a slider for c, that's fine. Let's go ahead and change this to a u instead. Oops, I know what's going on. There we go. All right. See, all that looks delightful. All right. And then what are we going to be doing here? We're going to be, we need the cube root. So y is equal to 1 over parentheses u1 plus u2. Boom. Let's go ahead and put parentheses out here. To the, put parentheses 1/3. Lord. Okay, let me erase these. Take those out. Make this a prettier color here. We'll go with purple. All right, and there's my solution. And again, you can mess around with this thing, okay, to see what's going on with that. But you don't have to look at this thing. right, on a calculator like this, on a graphing calculator. But you know, it's one of those things where it's like, well, let's just see what we're looking at here. Okay, so that's yeah, that's the solution to that problem. Okay, and again, it's like, well, tell me where all the discontinuities are. Solve this, right? It'd be a fun trig problem, right? Let's see. You know, do the line y is equal to 5 or something, and then like take your trig class to like solve these things, right? Set it equal to 5 and then solve. No thanks, right? Delightful. Right. Other substitutions, because this is getting terrible. So this is the other kind of solution, other kind of substitution that is going to be in your homework, okay, and maybe on a quiz. Okay, so I'm going to choose between Bernoulli and this other substitution. If you're really short on time and you're like barely hanging on to this, and you're like, I can't stand the sound of his voice, check the Bernoulli ones. I am more likely to ask you a Bernoulli one than anything else, because if you look at the course outcomes, right, the student learning outcomes, Bernoulli is actually listed, the other one is not. Okay, so this is kind of fun, it's kind of neat. Who am I kidding? It's not, it's terrible. But that's the one I'm more likely to ask is a Bernoulli problem, even though they're a little straightforward. That's okay. You should be allowed to have one or two that are straightforward, right? Okay. So what if you have like a square root of like 3x plus 2y plus 7 or something, or you have some kind of a terrible thing? This right here, this is the problem, right? This ax plus by plus c is the problem. Now, if b is 0, don't do this technique, because then you just have f of x plus g of x, and you might as well just integrate directly, right? So they go through and they say b is not 0. Okay, don't know why. Like if you had f of ax plus c plus g of x, you would just combine them into one function, multiply both sides by the dx, integrate both sides, be done with it, right? It's a separable equation. It's too easy. I say that without knowing what the heck I'm integrating, but at least there's a path forward. Okay, the integration might be hell, but you know, how to solve it is going to be straightforward. Okay, so here's our example. Okay, example 3. So we have dy by dx, right, is equal to, this is negative 2x plus y squared minus 7, and in this one we have the nice added complication of a initial condition. Okay, so the first thing we're going to do, right, is set u equal to this problem area. It's just the stuff inside of the function. Okay, that's why I put the gx outside. It's because the 7, we don't care about that. So u is equal to 2x plus y. And the nice thing is, with this substitution technique, the derivatives, right, that's going to be kind of nice. Du, right, is this going to be negative 2 plus y tick, derivative with respect to x, right, dy by dx. Okay, at this point, I tried to go through all of this. We're not going to do that. Okay, at this point, we're going to say u tick plus 2 is equal to y tick. All right, so when we go to substitute, we're going to say this is u tick plus 2, right, that's my dy, is equal to u squared minus 7. That's looking pretty good so far. Okay, so we have u tick, don't answer yet, it gets better, okay, is equal to u squared minus 9. And at this point, you can say, well, right, this is really, right, what is this? This is du by dx is equal to u squared minus 9. Why don't we just look at it like it's separable, right? I could just divide by this. Okay, I mean, technically it's Bernoulli, right? We could also do a Bernoulli, but rather than make yet another substitution of v is equal to u, right, to the 1 minus 2 and go through all of that, let's just say it's separable. Okay, so we have du over u squared minus 9 is equal to 1 dx. That's a physics integral. You gotta love those. This side, not a physics integral. Now we have, right, we have partial fractions here. So we have 1 over du over u squared minus 9, and we are saying that that is equal to a over u plus 3 plus of b over u minus 3, right? Because we can factor this. And I'm not really going to worry about the du. I'm just going to say we have a u minus 3 plus b u plus 3 is equal to 1. Okay, we're going to have a du at the end of this. We're not going to worry about that. Right, but a plus b is equal to whatever's on the numerator here, 1 du, and then we're just going to solve this. So we have a plus b is equal to 0. That's my u setting, right? And then we have minus 3 plus 3b is equal to 1, don't we? Did I set this? I did it backwards. All right, well, let's multiply this guy by 3. 3a plus 3b is still equal to 0. Negative 3a plus 3b is still equal to 1. Add those together because they didn't multiply here. That cancels. We have 6b is equal to 1. b would be 1 over 6. Looking at what a has to be from the first equation, I think by inspection we could say a must be negative 1 over 6. Okay? So let's see here. So we're going to say we have this whole thing, right? This guy here is going to come down, and we're going to say this is 1 over 6 times 1 over u minus 3, that's the b part, minus, and then we have 1 over 6, 1 over u plus 3, that's my a part. Okay, and this is equal to what? 1 dx. So let's go ahead and multiply both sides by 6. So we have 1 over u minus 3 minus 1 over u plus 3 is equal to 6. Okay, integrate both sides. There's a dx. There's a du. Okay. So we have natural log u minus 3 minus natural log u plus 3 is equal to 6x plus c. Okay, now we are in for just a little bit of algebra, by which I mean this is going to be the next 4 pages. Okay, there's a rule about logarithms, right? The rule of a over b was equal to the log of a minus log of b. We're going to do it this way. Okay, we have a log of a, log of one thing minus a log of another thing. So that is the log of u minus 3 over u plus 3. Okay, this is equal to 6x plus c. Let's go ahead and do that, right? Unlogify it. So we have u minus 3, u plus 3 is equal to, let's see here, we have a e to the 6x plus c, but we're going to say this is e to the 6x times e to the c, which is c e to the 6x. Okay. And now, I don't know if any of you ever had me for a pre-calc, we had to do inverse functions. This is the same kind of a shuffle that we're going to be doing here. So we have u minus 3 is equal to ce to the 6x times u plus 3. Okay. This is u minus 3 is equal to ce to the 6x times u plus 3 times ce to the 6x. Here's the shuffle. We have u minus u c e to the 6x is equal to 3c e to the 6x plus 3. At this point, you may have asked, why isn't he putting the 3 inside of the c? Because I got a c over here too, and I would keep them the same c's. Otherwise, we'd have a c1 and a c2 because they'd be different. Okay. So this is going to be u. We have 1 minus ce to the 6x. This is equal to 3 ce to the 6x plus 1. Okay, so this is u is equal to 3 ce to the 6x plus 1 all over 1 minus ce to the 6x. But wait, don't answer yet, because we still got to unravel what u was. Okay, so if we go back up to here, what the heck was u? U was negative 2x plus y. Thank goodness. Negative 2x plus y is equal to this mess. Ce to the 6x plus 1. 1 minus ce to the 6x. Add the 2x to both sides, so we get y is equal to 2x plus 3 ce to the 6x plus 1 over 1 minus ce to the 6x. And we're still not done, because we had this delightful little condition of y of 0 was equal to 0. So y equals 0 when x equals 0. So let's plug in when x equals 0. So y is equal to 0 plus 3. This is c e to the 6x, e to the 6 times 0. That's just going to be 1 plus 1, isn't it? Okay, this is plus. And then here we have 1 minus, again, c. Okay, and this, by the way, this is equal to 0. Okay, so we have 3 c plus 1. 1 minus c is equal to 0. Multiplying both sides by the 1 minus c's. So that flushes. Okay, that's out. 0 is equal to 3c plus 3. Actually, we could divide both sides by c, 2 or 3, couldn't we? We could. So it's just going to be 1. Put the 1 on the other side. We have c is equal to negative 1. All of that. Okay. So here we go. We have 2x plus 3. And I'm just going to reverse the order, because I will keep the negative of this. That's going to be 1 minus e to the 6x divided by, and the same thing over here. This is going to be 1. C is negative 1, so this is going to be 1 plus. 1 plus e to the 6x. That equals y. All right. And there we go. That's our answer. All right. Again, let's go ahead and take a look at it, because again, I think it's just kind of neat to see what these things come out to be. Okay, let's kill all of this. Again, all those college algebra students, they don't know what they're missing here, right? So let's go ahead and say U1 is equal to, what are we going to do here? We're going to do this as a 3, 1 minus 6x. So this is 3, 1 minus e to the 6x. It's a big e to the 6x. It's really big, really fast. Okay. U2. Oops, I want U2. And that is equal to 1 plus e to the 6x. And again, that's going to go shooting way up, because e to the 6x is huge. Okay, and then we're going to say y is equal to 2x plus, and we're going to have u1 over u2. Right, we'll cancel this guy out. We'll cancel this guy out. Okay, and there we are. Okay, kind of want to do this. I just kind of want to say here's a C, and then here's a C. We could add a slider for C, and kind of let us slide this thing around so we can, oh, look at that. That's kind of neat. Let me just kind of slide this around here. Okay, so that's yeah, that's what this looks like. Kind of an interesting looking function here, but there we go. Okay, scroll in a little bit. See, it goes to my point. It's great. What your poor college algebra students solving logarithms and figuring out, like, hey, what's y? You know, find all solutions where y equals 1. I can go through and do all of that. No thanks, right? Okay. So yeah, that is our substitution techniques. You have a couple of this form on the homework. Okay, Bernoulli is the important one. So like I said, if you have limited time, check out Bernoulli's. You know, spend your time on that. I may show you another one in an optional video. It was not on your homework. They didn't ask you any of those, but it's a substitution. It's either y is equal to u times x, right? Or x is equal to v times y. Okay, that's the substitution. I was like, well, and it's very useful when you have, right, a bunch of functions that contain this, or a bunch of functions that contain, right, these guys. And the differential equations book that I learned out of had a whole section of doing these delightful things. Actually, they had a whole section on top of this that dealt with even more substitutions like this. Okay, so I tried to do my best to like show you guys the real general ones, because there are a lot of specifics. Okay, there's like the big book of, if your differential equation has this form, then you're going to use this particular substitution, or you're going to use this particular technique. And that really turns this class into a recipe class rather than, you know, it's like taxonomy. If you took one of the biology classes, right? Is it animal? Is it vegetable? Is it you know, is it fungus? Is it? I think there's another one now too. And then you start like going down this little tree to figure out what actually is going on. And like, not really into that for a math class, of kind of diagnose what kind of a problem it is, and then you look it up, like how do you do it, and then you solve it. Okay, I mean that's what really happens, but we're going to try to spend more time on, like, you know, the solution methods. If somebody tells you like, here's how you can solve it, we'll practice solving it. Okay. So yeah, those are our solution methods. Those are our substitution methods. Again, don't get overwhelmed by them. You've got two. Okay, you've got the ax plus by plus c, and you've got Bernoulli's, and that's linear, sort of, but with a nonlinear y term. That's it. Okay, and it's going to be to a power. It's not going to be like a logarithm of y or some crazy thing like that. If that does happen, you know, so what do you do with, you know, you've got this, some function of x, and you've got a different function of y. To tell you the truth, I don't really know what the best solution is. If I had like some kind of a logarithm of y in here, I would go back and use a Taylor series in y and say, well, that's going to be, this is my Taylor series for y. How many terms do you want? And then do it that way. Okay, if it's like, you know, sine y, you could say this is y minus 1/3, or 1/3 factorial y cubed. Pull this one over on the other side and then solve it as Bernoulli for y cubed. Okay. If they say, well, no, we need two terms, I'm like, I don't know what to do then, because I can't, Bernoulli is not for like y cubed plus y fifth. Okay, it's not gonna, you're not gonna get anything out of that. Okay, I'm gonna stop talking and leave you with that, and I'll put your homework up. All right, thank you.